In this video, we are going to learn about the properties of trigonometric functions. Now, you're going to want to have your unit circle handy as we talk about this, because I drew a little simplified version at the bottom left of my paper, but you can use the actual unit circle to see everything involved. Now, at the top, I went over again, just like I did in the last lesson, like what sine, cosine, tangent are equal to based off a point on that unit circle. Now, I included that x cannot be equal to 0 or y cannot be equal to 0 if that was in the denominator of that function. That's going to be very important as we discuss domain and range of these functions. Now, as I discuss domain and range, we usually notice x and y, and since theta is not x or y, I just rewrote these functions to include y and x so we can talk about domain and range. Now again, this is actually how you spell these trig functions in case you were wondering. Now, the domain for sine of x, if using a unit circle, is whatever you can plug into it. So what angles can we use? Now, since we're not worried about what we get out over here, you can plug in any x value you want. So meaning the domain is all real numbers. So any angle you plug in can work. Same thing for cosine. Since there are no restrictions with what can come out or what you have to worry about with the output of which the x coordinate is, the domain is all real numbers. Now, where this starts to become a bit more of an issue is when we get the tangent of x, where we know it as y coordinate or the x coordinate. And we know that x can't equal to 0, but there are spots on our unit circle where the x coordinate is 0, and that happens at pi over 2 and 3 pi over 2. Now, since this thing is continuously rotating around, I'll just use the counterclockwise direction. Or you can go clockwise. It's at pi over 2, 3 pi over 2, and then another half rotation, we get 0 again, and then another half rotation, and another half rotation. And so it'll continue on forever. So the way we write our domain for tangent is that we say that x cannot equal pi over 2, but now it's every half rotation following, or if you went backwards, another half rotation in the other direction. So we just say plus n pi. Pi for that half rotation, and n being for any integer you want to pick to put there. So 0, 20, negative 17, that's an x value we cannot plug into tangents. So using that same logic, cosecant, we know that y can't be equal to 0, which happens at 0 as well as pi and 2 pi and every half rotation from there. So 0 plus n pi, but since it's just 0, we can say x cannot equal any integer multiple of pi. For secant, again, x cannot be 0, so we'll have a very similar domain to tangent, where x cannot equal pi over 2 plus n pi. And for cotangent, we know that y can't be equal to 0, so we'll have a similar domain to cosecant, where x cannot equal any integer multiple of pi. So that's your domain. Now, range is what we get when it's equal to. So what y's can we get for sine? Now, looking at our unit circle, we see that y can go as low as -1. So we can put -1, 2, and as high as 1. That would be the range of sine. It can't go past 1 or -1 in either direction, but it has all these values in between that it can hit. Same thing for cosine. It's between the x values of -1 and 1, so its range will be from -1 to 1. Now, tangent, something very interesting happens. Since we have it as y over x, as you go through and test a bunch of x and y values that do exist on this unit circle, you'll start to realize that you can get any y value that you wish. So the range is all real numbers. And just to go over the interval notation for all real numbers, that would be -infinity to infinity. So any value you can think of can be plugged in for the range. You can get from plugging in some angle into tangent. Now cosecant's a little bit different. As we are only using 1 over y, as we start to plug in all these y values between -1 and 1, we actually realize that we can get any number we want to besides those values that are between -1 and 1. Because in order to get like 0.5, you would need to plug in 1 over 2, but 2 is not a y value that we can use. So our range for cosecant ends up being negative infinity to negative 1 union 1 to infinity. So it's just everything except negative 1 to 1. You'll see that same process happen for secant, because the x's are bound to negative 1 to 1. It'll have a very similar range to cosecant. Again, if you want to understand this, start plugging in values in between negative 1 and 1. You'll see that they can get very large and as close to 1 as you could possibly get, and then equaling 1 or negative 1 when you plug those values in. And cotangent, since it uses x over y, has a very, very similar range to tangent. It's all real numbers, which means negative infinity to infinity. It's very important to know what values you can plug into a trig function as well as what values you can get out from it. This will help with equation solving and graphing in the future. Now let's talk about the period of a function. Now these functions start to repeat themselves, mainly since we're rotating around a circle. Eventually you're going to get the same angle shape again, which means that trig function is going to be the same value again. Now for sine, you won't see it start to repeat a pattern. If you look at just the y values, you'll see you go from 0, square root 2 over 2 to 1, to square root 2 over 2 to 0, which hasn't repeated anything yet because we go to negative square root 2 over 2, to negative 1, to negative square root 2 over 2, and then back to 0. Then we'll continue that cycle every time. So we say the period of sine is 2 pi because it takes a full rotation before you repeat the same pattern. Same thing for cosine. It takes a full rotation before you repeat a pattern. Now tangent is a little bit more unique. It goes from 0 to 1, whenever you put y over x, to undefined, to negative 1, then back to 0. And then 1, undefined, negative 1, back to 0. So it only takes a half rotation before you repeat its values. So its period is just pi. Cosecant, since it's 1 over y, since the period of sine is 2 pi before it repeats y values, cosecant will be the same thing. Same thing for secant because it's 1 over x, and cotangent being x over y. Since y over x was only a period of pi, then x over y is also just going to be a period of pi as you go through and check. Which means that if I look at sine of theta, if I add 2 pi to the angle on the inside, it is the same thing as just sine of theta. Those are both the exact same function. I can say the same thing for cosine. Theta plus 2 pi will just give me cosine of theta. But tangent, I can say as if I put theta plus pi, that's the same thing as tangent of theta. And again, any multiple of these as well. We discussed earlier with the domain that sometimes any multiple of that will also reveal the same angle. Cosecant of theta plus 2 pi will equal cosecant of theta. Secant of theta plus 2 pi will also equal secant of theta. And cotangent of theta plus pi, since that's its period, will just be cotangent of theta. Again, period being the amount of time it takes until you repeat yourself. So in this case, it takes a full rotation for 4 of the functions, while only a half rotation for cotangent and tangent. Now, last thing to talk about is the sign of these functions, depending on which quadrant we're in. It can really help with learning like your unit circle values, as well as just understand what the value of a trig function would be based off its angle. Now, starting off, since x and y are positive in the first quadrant, all of these trig functions are positive in the first quadrant. Now, in the second quadrant, we will find that x is negative, but y is positive. So meaning anything that involves only y, which is sine and cosecant, will be positive, while anything involving x is going to be negative. Even as y over x, that will be a positive over a negative, or a negative over a positive. In quadrant 3, both x and y are negative. So any of them just involving just y or just x will be negative, but if they involve both, that double negative makes it a positive. So tangent and cotangent will be positive, while every other function will be negative in the third quadrant. And lastly, in the fourth quadrant, x is positive, but y is negative. Just like with the second quadrant, anything that involves just x, cosine, and secant will be positive, but anything else is going to end up being negative. Which leads us to a very curious thing. You'll see that sine and cosecant are paired up. Cosine and secant are paired up, and tangent and cotangent are kind of paired up. Because if one's negative, then the other one's going to be negative, since they are reciprocals. But a nice little pattern happens where in the first quadrant, all the trig functions are positive. In the second quadrant, just the sine trig functions are positive. That includes cosecant that goes with it, since it's reciprocal. In the third quadrant, only the tangent function is positive, and in the fourth quadrant, only the cosine function is positive. Again, keeping in mind that I've paired them off to make this work. So it creates a kind of fun acronym. I like to remember, always serve toasty crumpets. It's a fun one. Or if you look at it as a backwards U, it spells out X. And it's a cool way to remember which quadrants are positive for which trig functions. Now you know some of the properties of trigonometric functions.